All right, go ahead, Moshe.
Okay, so I don't know what. Strange. This. Now you can hear me?
Yep.
Okay, great. So I'm not sure what you heard before or not. Anyway, I'll just proceed. So this is a generalization of some work that was done by Rahim and Freitag and other people from the differential setting to the different setting, and it's a generalization of one component, namely the binding group, which in the difference case is a bit more complicated. So that's what I'm going to talk about. Okay. I don't know what happened. It used to work before. Um, okay. Um, okay. So the basic object is a rational dynamical system, which is just an algebraic variety, along with an endomorphism. And the endomorphism, what makes it slightly special is that the endomorphism is rational rather than regular. So dominant rational map from V to V, both over some field K. And my field is going to be always of characteristic zero, and for convenience also algebraically closed. So the algebraically closed is a bit is not a serious issue, but in most of the things, but the characteristic zero is. Um, so that's just a dynamical system, which is quite standard. But in model theory, we also like to work with fibers and doing some induction, and for that we often need to pass um, to a slightly more general setting. Namely, we have a field with an endomorphism already. The base field is has an endomorphism, and then we have a twist for the variety. And the analog or the generalization of a dynamical system is what we call a rational sigma variety, which is a variety V over K, but equipped with a dominant rational map from V to V sigma, okay, to the twist. Which is, okay, geometrically, you can also think about it as just a relative situation. You can imagine that K was the field of functions on some rational dynamical system, and then we have a map from V to that variety. Okay, and yeah, so the previous situation is when sigma is the identity, and I denote by this boldface L just the affine line with the trivial dynamics. So what are we interested in? Usual dynamical system questions, but with a twist. So, for example, if I'm talking about an invariant subvariety, that means that I have a subvariety defined over the same field K, and the phi should preserve it in the sense that it takes Z to the twist of Z. Okay, orbits, we take some point and start applying phi to it. So this mostly makes sense for just dynamical systems. Relations among different sigma varieties, and in particular invariant functions are going to play an important role. And not really in this lecture, but related is algebraic relations among trajectories, among solutions to the different equations. Okay, so this is so just two examples. This is not an example of something very special. It's just to show that if you talk about rational issues in usual algebraic geometry, it just means that you usually can just pass to some heuristic open subset, and then you get something regular. And in this situation, it's not the case. It's not the case that rational dynamical system is just a regular dynamical system on a smaller an open subvariety. This is an example. So in this example, it is not defined on x equal to 1, but then if you remove it, then it's also not defined of x equal to 2 and so on. Okay? Okay, and the other example is just to show that things can be.
Moshe, we might have lost a little bit of audio.
Did you lose it completely?
We lose you and now we hear you twice.
Yeah, because
yeah, now we can't.
But you heard me just now.
Now a little bit, but it's sort of not quite optimal.
Okay. How about if I speak like that?
Yeah, that's good.
Maybe I'll take off this then. Okay, so I was saying you see the second example. So this is from the paper by Chatsidakis and Nurshovsky. It's an example they analyze, and you see it's a very simple looking example. You just pick your favorite A, which is not 0, and you ask the basic things about this example, and it's not that easy to figure out. I mean, it's possible, but it requires work.
And sorry, just to hear, here you don't allow for invariant subvarieties where you extend the base field, or you consider that case too?
So it's it's a good question. I mean, I could consider both. In this generality, it doesn't really matter that much because I mean, if extending parameters, I could also look at higher. See, I do want to have Cartesian powers. Maybe I didn't write it. Okay, I consider I don't extend parameters, but I do consider all Cartesian powers of the varieties that I'm interested in, right. And so it amounts to essentially the same.
Yeah.
Okay. Okay, so this is the result. So for people coming from model theory, it just asserts that there is a certain variant of the binding group in the appropriate notion of internality. So what it says is if V is isotrivial, which I'm going to explain later, there's an algebraic group that acts birationally on V, identifying. So the action identifies the elements of G with birational automorphisms of V over L. Okay, and that's for any field extension. So I need to explain what is this group, what is these birational automorphisms, and then of course also what is isotrivial, and probably and say why is this interesting. So I will start with the birational automorphisms. So birational automorphisms are just automorphisms in this category. Okay. So this is just, oops, yeah. So this group, the Birke of not bold V, is just algebraic geometry. Is birational automorphisms of VK, often a big group. Now, if I want to take into account the dynamical structure. So I consider all the invariant subvarieties of all Cartesian powers. I need to be a bit careful because I'm working in the birational category, so I want them to project dominantly on all the factors. And I look at all the automorphisms, at the subgroup of all the automorphisms that preserve these invariant subvarieties when where the action is diagonal and the action on L is trivial. Okay, so I take an element of I take a birational automorphism. It acts on powers of V. It acts trivially on the affine space, and I consider only those that preserve the invariant subvarieties for the dynamics. Okay.
What's L here, Moshe?
So L is the affine line with trivial dynamics.
Mm-hmm.
Okay. So this is some subgroup. Okay. Now, what do I mean by birational action? I just mean a birational map, action map from G cross V to V. But I want it to be defined on all elements of G. Okay. So for every element of G in any field, I get some birational automorphism of Vk, and so I get a map from the k points of G to Bir kv, and the claim is that this map identifies the points of G with this group that I defined. Okay. Yeah. So this example is not an example of the theorem. It's just an example of a birational action. So you see, the additive group, it has an obvious action on A1, but it also has this action on A1, which it's not regular. It's birational, and again, it's not the case that it restricts to a regular action on some open subset. Okay. So this is an example of this kind of action. Another example is an example of the theorem. It's a familiar example where the V is the affine space and phi is a linear map. And then what we're talking about here is essentially the difference Galois group associated to the linear difference equation. Okay. Yeah, and I didn't write it in the theorem, but actually G is not just an algebraic group, but it's also equipped with dynamics, and the action is an action of the action of G on V is an action of dynamical systems. Okay, or the sigma varieties. Okay, so now I want to postpone talking about isotrivial. I want to talk about some applications. So the first application is to the case of dynamical systems. So sigma is the identity, and you could ask, suppose you have a dynamical system. Is there so it's just one endomorphism? Or automorphism, and you could ask, is there an algebraic group action that this dynamics comes from? Okay, so does it act like an element of some algebraic group with an algebraic group action? And the answer in this isotrivial case is yes. This is a result that was obtained by Belmus and Saturnino, but with totally different methods, and from the perspective using the theorem that I just explained, this is essentially trivial because okay, so the statement is that in the isotrivial case, the dynamics is always translational, so it always comes from a group action, at least up to a birational equivalence. And the explanation is very simple because the dynamics, the map on V is an element of this Bir KVL group. Okay, it commutes with itself. So it's automatically an element of the group, namely of an algebraic group, namely the binding group. Okay, this group that is guaranteed by the theorem. Okay, and now this this result, okay, it's for we wrote it in the paper for the case of where sigma is the identity, but actually it's true in almost complete generality in the isotrivial case. You need to understand how to formulate it, but it's definitely true beyond the case of where sigma is the identity. And the theorem itself has some well-known conclusions. So one of them is what's called the Zariski dense orbit conjecture, which just says that there is a point whose orbit is dense, and this is under the assumption that, of course, that V is isotrivial and also weakly orthogonal in the sense that it doesn't have any invariant functions, rational functions. Okay, so this just follows from the translationality. Okay, so that was weakly orthogonal. What is just non-weakly orthogonal? So orthogonal means that you have you don't have an invariant rational function even after a base change. Okay. Now, of course, if you base change to W, then W itself could have invariant rational functions. So we want to ignore them. So you're saying every invariant function actually comes from W. Okay. And so this is you can think about it as a geometric version of saying weak orthogonality. So even after base change, but of course notice that the base change here is by a difference variety, by a sigma variety. Okay, so this is not just a question of rationality in the sense of algebraic geometry, and you can ask. Suppose you want to check if V is orthogonal to L. How far do you need to go with W? How complicated W needs to be? It seems like a difficult condition to check, but actually, it turns out two things. First of all, that you just need to take W, which is Cartesian powers of V itself, and then you also have a bound on the number of copies that you need. So the bound is written here, and this is just again a result that one of the main results that was obtained by Freitag and Musa, and then later the other variants by some other people. And the method is exactly the same. Once you know that you have a binding group acting, you just use a classification of how transitive an action of an algebraic group can be. Okay. So again, these are all corollaries, like immediate corollaries by previous methods of the fact that you have this group acting and the nature of the group. Okay, and another application. I guess I'm almost out of time. So one question you can ask is: are there you could always consider maximal proper invariant subvarieties of your sigma variety, and you might wonder if there are infinitely many of them. So one case where there are infinitely many is when V is not weakly orthogonal. So if you have an invariant function, then its fibers are going to be maximal and maximal invariant, and infinitely many of them. And the claim is that in the isotrivial case, this is equivalent. So this is This is called the Dixmuir-Moglin question. Okay, there is the proof, the sketch of a proof here. It's not complicated, but maybe I'll skip it. So let me just say what is isotriviality. So isotriviality is what is analogous to what we call internality in model theory, but it's slightly different, and it can be explained completely geometrically. So, and the idea is, again, after base change, you want to say that after base change, the dynamics is trivial. So this is how it looks like. You have a family of maps parameterized by this W, mapping V injectively into the trivial dynamics. And of course, if there was no W, then it just says that V has trivial dynamics. But with the W, it could have non-trivial dynamics, and still be interesting. Okay, so some examples. Take A1 with phi of x equal to x plus 1, and then you just take W equal to V and G the difference between x and y. So this will be fixed. Another familiar example that is used in the Galois theory of linear difference equations is V is equal to the affine space, and phi is linear. Okay, it's a linear map, and then you take W to be the set of bases for V. And you can generalize these examples. You just take V to be an algebraic group, and then phi to be action by some element of this algebraic group, and so for some fixed A, and then you can take W equal to V again. And this is this is a generalization of both of these examples, both previous examples, but also in some sense that the theorem says that this is essentially the most general example. Okay. So one thing you can ask is, how common is it to have an isotrivial dynamical system or an isotrivial sigma variety? Maybe the theorem doesn't say much about sigma varieties. Well, I don't know how to quantify it, but there is a relation. There's a strong relation between being isotrivial and being non-orthogonal to L. So, of course, if you are isotrivial, then you're definitely non-orthogonal to L. And the converse is not true, but something is true in the converse, which is if you are non-orthogonal to L, then you have a surjective map to some isotrivial sigma variety, which is non-trivial, which has a positive dimension. And this is again, the proof we have in the paper is model theoretic, but it's actually not that difficult to give a geometric proof. So I sketch it. So the assumption that V is non-orthogonal means we have a W and some rational function from V cross W to L, which does not come from W, right? So now we can transpose it. This function f gives a map, an equivariant map from V to the space of all functions from W to L. Okay, so this is an infinite dimensional space, but it's a union of finite dimensional varieties, and it has a dynamics that comes from precomposition with the dynamics on W. So we get a map like this, and we take Yeah, and we take the image of this map. So the image is already finite dimensional. And I want to say that this image is isotrivial, and the isotriviality is given by just the evaluation map. Okay, so we have an evaluation map from W across this H to just L, right? We evaluate a function on an element of W, and then we can just restrict it to the image of F tilde. Okay, so this is in a sense a typical example of isotriviality, and the fact that F does not come from W exactly means that that V bar, the image, has positive dimension. Okay, so I don't know how what's going on with the time. If
I think you can.
I don't know.
You can.
I can. Okay, so someone will just stop me when I go over. Okay, so I want to say something about the model theory. Okay, why do I want to say something about the model theory? There's several reasons. One of them is that our methods are model theoretic, and most of what we do can be completely translated to geometric language. But okay, we didn't try too hard, but some of the things are not that easily translatable. And but another reason is, for example, if you look at these conditions, so you say, okay, so we have basically two options: either either our sigma variety is non-orthogonal to L, and then okay, we can project it to something which is isotrivial. So maybe the isotrivial case is interesting. But what happens if it is orthogonal? And here there's a lot of machinery that was developed model theoretically, and the case of being orthogonal to L is okay, is in some sense understood, or at least can be analyzed using some model theoretic methods. Okay, so what is the model theoretic setup? So we look at difference fields. We consider so we consider them in the language where we add a symbol for the automorphism. Okay, and then one thing is once we have a sigma variety, we can associate to it a formula, or a quantifier-free formula, which we think of as a definable set. Namely, I just say sigma of x is equal to phi of x. Okay, so the set. So if you imagine the. Okay, so this is some formula. There's also a type. So it turns out because we work in the rational category, we don't really want to look at all solutions of this equation because our maps might not be defined on some of the solutions. So we look at generic points, generic in the Zariski sense, that satisfy these equations. Okay, so we have a canonical quantifier-free type associated to V, which we call the generic type of V. Okay, now why is it? In what sense is it a type? Why is it consistent to look at all these formulas? Why is there a generic point that solves the equation? So this follows from the analysis of universal domains for difference field. So namely existentially closed difference fields. Okay, and one of the things. So one of the things that the analysis tells us is that there is a dense set of solutions of points in this universal domain that solve the equation. Okay, Geometrically, of course, this equation corresponds to some difference equation or recurrence relation. That's the intuitive picture. It's not the case that elements of U are actually functions. Okay, so in particular, we have the fixed field, CK, which is the sharp points of the field of L. Okay. Yeah, and as I said, there is an axiomatization of the class of existentially closed difference field, which is called ACFA. So I want to tell a few facts about ACFA, which all come from the foundational work of Chatzidakis and Olshovsky about this theory. So first of all, there are axioms. It is an elementary class, and the most important axiom implies that really the sharp points are the risky dense in the variety. The axiom is actually more general, but that's what we need. Okay, somehow one of the main points for us is the elimination of quantifiers. So this asks the question of whether every formula is equivalent to a formula without quantifiers, but the answer is no. Okay, so the answer is, in this theory, not every formula is equivalent to a quantifier-free formula, and this makes things quite a bit more interesting. But there is some understanding of what are the sets that are definable with quantifiers. They're quite simple, given that we don't have quantifier elimination, but still the situation is complicated. So again, this example, you look at the formula sigma of x is equal to x squared plus 1, and you ask, is there a formula that defines a subset which is both infinite and co-infinite? Okay, so not as a risky constructible subset. And the answer is that there isn't, but it requires work. Okay, also something that complicates matters, the definable functions are quite far from being just rational functions. So every rational function is definable, but there are also more complicated definable functions, and this complicates matters. Okay, elimination of imaginaries means that there are definable quotients, which is in principle a good news, but because there's no elimination of quantifiers, from our point of view, this is not directly helpful. Okay, okay, and then the main part of their work is to show that there is a well-behaved rank on definable sets, and you can analyze finite rank definable sets by sets of smaller rank, and the rank 1 sets are satisfy what's called the Zilbert trichotomy, some version of the Zilbert trichotomy, and which is basically what I said before. If you are orthogonal to the constant, sufficiently orthogonal to the constant, then your modular, which says okay, which has some interesting implications. Okay, and isotriviality is it corresponds, as I said, to what's called internality in model theory. So internality is a completely abstract notion, and it says something very similar to the way I defined isotriviality. It says that the definable set, which in this case is just, I want to think about V sharp, is internal to some other definable set, which in my case is L sharp, if over parameters there is a definable embedding Okay, it's supposed to be L sharp. Okay. Now the problem is, yeah. So why is it important? Because then completely in a completely abstract way, one produces a definable binding group, a definable Galois group, which is analogous to the group that I'm talking about. But the complications come from well, two sources. One is that, as I said, there's no quantifier elimination, and so the group that is the general group that is provided by model theory is first of all not the correct one, and second, it's not algebraic. And the other issue is that we work with rational maps, so which means model theoretically that we want to work with types rather than definable sets. Now there are various versions of internality, and some of them do work with types, but we have to because we have both of these complications together, we had to adapt to this setting. Okay, so I made some comparison of the differences between what happens in abstract model theory versus what the situation that we have. Okay, so internality, as I said, it's replaced by isotriviality, and here it's a more strict condition because I require. Okay, first of all, it's weaker because I only talk about the generic type of V. But on the other hand, I require that the internality is given by a quantifier-free formula, by not just a quantifier-free, but rational. Okay, this trivialization is given by a rational invariant function, whereas in abstract internality, I just need a definable map. Now, the second difference is the group of automorphisms. So in the classical situation, the group of automorphisms that we look at is just the automorphisms of the whole universe fixing the L sharp of, right? So fixing the elements of the fixed field pointwise. And then we just divide by the subgroup, by the normal subgroup that fixes also V, the set that we're interested in. So altogether, okay, so we don't want to, if we have an element of the automorphism group that fixes all elements of V, then we want to consider it as the identity. And so altogether we get a group that acts on V and acts trivially on fixes the elements of L, but each element in this group can be lifted to an automorphism of the universe. Okay, and this is not what we want here, because remember that there's no quantifier elimination. So the requirement that the automorphism lifts to the universe means we preserve too much structure. Okay, we don't want to preserve. Remember we wanted to preserve all the invariant subvarieties, but we don't want to preserve a more complicated definable subset. Okay, so we just want to preserve the quantifier-free structure, and then as a result, if you do use the general machinery in the difference setting, you get a group which is first of all, it's pro-definable rather than definable. It's an intersection of definable subgroups, and it's not algebraic, so it's not going to be useful for the applications that I mentioned. Whereas we get an honest algebraic group, again equipped with dynamics, and the generalization of the binding group is going to be just the G sharp for these dynamics. Okay, so here I added an example. This example just it illustrates the difference between the two groups and the two structures that you preserve. If you look at this this dynamical system. So what we want so this is just a linear difference equation over the constants. We know what we want the Galois group to be. It should just be GM, right? Because the solutions are not algebraic and don't satisfy any algebraic relations. So we want the group to be the multiplicative group. But if you consider the full definable automorphism group, okay, so if you have a solution, you can take a square root of it. Okay, and the square root will satisfy either the equation sigma of x is equal to square root of 2 times x, or minus that. Okay, and it follows from the axioms that both of the options occur. So we have an interesting non-quantifier free definable subset of the corresponding sharp points, and the model theoretic automorphism group preserves this subset. Okay, and so the group that you will obtain that this way is going to be, so of course you can continue in taking more roots, and the group that you obtain this way is going to be some infinite index subgroup of the multiplicative group. Okay.
So maybe we'll, yeah,
I think I'm
here,
finished.
and then you can do your conclusion within the question. So let's all thank Moshe for his talk. Thank you, Moshe.
Thanks. I'm sorry again for the technical issues.
All right. Do we have any questions for Moshe? Feel free to unmute yourself and ask.
Hi, this is Michael. Can you hear me?
Yes. Hi, Michael.
Yeah. So this question of a finite number of maximal invariant sets, do you have
Right.
any results saying that if there exists more than so and so many, then they're an infinite number?
Oh, we definitely don't have them. And
You know, in the differential case, let's say on the plane, there are classical results like that.
well, the method that we use definitely is not going to give that, because we just use model theoretic compactness.
Right.
Yeah, we just conclude that the union of all these sets is definable, and so it must be a finite union.
Yeah.
But yeah, but we could. I mean, I don't expect we could actually get precise result, but maybe we could somehow get conclude that a bound exists if you have a family or something like that. But I would need to think about it.
Okay.
Thanks. Any other questions for Moshe? So I have one. So the bound you get for witnessing non-weakly orthogonality is for the autonomous case, you get that n is 2. Can you improve, you think, the non-autonomous case? Or is that optimum?
I think we tried to figure it out and didn't get anywhere. I think we don't know that we can't improve.
I see.
Yeah, but as far as I remember, it was we left it open.
Okay. Any other question for Moshe? If not, let's thank him again. Thanks, Moshe.
Yeah, thanks for having me. Nice to see everyone.
And we see you all. I think we do have a talk next week.
Thanks.